Oh, one thing which is if you have any questions, leave them to the end of the session. Yeah, or you can just type them into the chat.
Nice. Okay, so let's stop today. Like it's the final session, and yeah, we will wrap up today. So, so yeah, I mean, so in the past we have talked about classical error correction, basics of quantum error correction, and the stabilizer formalism. Uh, then we had, like Tori code. Then we also discussed our introduction to topology, topological quantum codes, bosonic codes, subsystem codes. Then we had a session on approximate quantum error correction, fault tolerance, and decoders. And today we will basically continue talking about decoders for quite some time. And then we will talk about connections with many-body physics and theoretical computer science, plus some discussion about black holes. Okay, so so this is the overview. I will discuss what like we discussed last week. Basically, this should not be last week, last session. Then we will discuss about decoders and then connections with like many-body physics and TCS, and then black holes. And finally, summarize here. Nice. So let's recap. So we discussed before that if you have, let's say, I mean, so this is the condition, like for the Neal-Laflamme condition for error correction that we discussed before. And here, this C matrix, this has to be, this should be a Hermitian matrix, and this delta is basically Kronecker delta function. And we mentioned that what if, like these conditions are not exactly satisfied, then can we still do error correction? And indeed, there is a notion of error correction called, like approximate quantum error correction. So in those cases, the quantum error correction criteria are not perfectly met. And actually, there is no analogous criteria, condition in the analogous thing in the classical error correction. And in some sense, this approximate quantum error correction arises from, you can say the near orthogonality of some quantum states. So there's this paper by Debbie Leung and others, which, talked about approximate quantum error correction. And in this paper, they basically, so we know that the 5 qubit is the minimum number of qubit you need to encode one physical qubit with distance 3. But in fact, if you are interested in not perfect error correction, but only approximate quantum error correction, then you can have you can have less resources and you can still do error correction. So there is 412 code that we discussed. And you can have, similar condition, but, they are approximate sufficient condition that you can get for approximate error correction. Then we also talked about, fault tolerance, where we said that, let's say you have some circuit, and here if each component fills with probability at most P, then error at the output is, of the order P. And we said that how does, error propagate? So let's say you have a C naught and you have some error here. So the same error will propagate here. And here is a table which you can use to infer, how does error, error go from, propagate across circuits. So this is nice. And then we also talked about, basically concatenation, and used it to define, come up with basically a toy version of threshold theorem for quantum computation, which basically says that no matter, whichever error you have in mind, as long as the probability, the failure probability for every circuit component is below some threshold, using only using just only polylogarithmic overhead, you can achieve that error. And then we also talked about the Easton-Neal theorem and how to circumvent this theorem using techniques. I mean, we just mentioned a few techniques, that the code switching, code drift, and magic state distillation and so on. Then we talked about, the decoders, where we said the task of a decoder is to find the appropriate equivalence class. So given some error, there can be, multiple strings which correspond to the, the same error. And with the same boundary. And in fact, like you can come up with a correction operator, but let's say if your correction operator is such that it ends up like applying a logical error, then like that's a problem. That's not good. So you can have no error, or you can have like Z1 bar, Z2 bar, or Z1 bar, Z2 bar. And the task of decoder is to find the appropriate equivalence class. So if you find the right equivalence class, then you are okay. Otherwise, like it's not good. After that, like when we just briefly mentioned, there are like many different decoders, and you can look at this paper to have a get a deep understanding. So we will keep talking about decoders today. And meanwhile, like I would appreciate if more people, like turn on their camera so that it becomes like more human. So yeah, I mean, so let's talk about like decoders. And meanwhile, like please turn on their camera, like that is much appreciated. Yeah, thanks. So let's like I mean, so we talked about like Tori code, and in the case of Tori code, like we like if you recall from the second tutorial, we mentioned that I encoded logical operator must commute with all element of the stabilizer group, must not be an element of the stabilizer group, and must satisfy the commutation and anti-commutation relation of the poly operators they encode. So you have, like Z, you have X, and then you have, Z2, X2, and so on. Then we also talked about, like how to do error correction via Tori code. And we basically, you can, as long as the error, so let's say this is the error, and this is your correction operator, as long as together they form a, like a trivial loop, you are okay, because that trivial loop corresponds to a stabilizer. And the task of a decoder is to find the appropriate equivalence class. Basically, you should not end up wrapping around, like it should not correspond to a non-trivial loop. Whenever it corresponds to a non-trivial loop, your correction operator plus the error, then it will lead to, some logical error. Yeah. And so the idea is that, like your correction operator should be, like the error operator plus some boundary. And if that is not the case, then you will have a correction failure. And the task of a decoder is effectively in the language of topology to return the appropriate homological equivalence class for the error consistent with the observed syndrome. Very nice. So, so basically, you can say that if if the decoder outputs a correction operator from the wrong equivalence class, then it can be termed as a failure for the decoder. So let's today, like discuss how to decode. So we will take an explicit, like scenario. And so I think just a few days ago, like 2 weeks ago or something, there was this paper came like Sparse Blossom by Higgett and Gidney. And I have taken some content from this paper, and I will discuss it here. So there are a few objects that you need to take into account, like which people normally talk about when they like I mean at least in this paper. So like detectors, logicals, like measure errors and so on. So I will discuss what these things are. So basically, a detector is nothing but a parity of measurement outcome bits in a quantum error correction circuit. So here, like your detector is just M1. Here your detector is parity of M1 and M3, and here the detector is like parity of M2, M3, and M4. So detector 1 is concerned with this region because M1 only is concerned here. Detector 2 is concerned with the region which correspond to M1 and M3. Detector 3 is concerned with the region which correspond to M2, M3, and M4. And so basically just a parity of certain measurement outcomes. So it's 1 if the observed parity differs from the expected parity for a noiseless circuit, and it's 0 otherwise. So yeah, we discussed that. And any error within the circuit which anti-commutes with its type will cause the corresponding bit to flip. So if that happens, then basically that we will call that as a detection event. Next, there is the notion of logical observable. So logical observable, I mean, from before, but in the case of circuit, it's basically nothing but linear combination of measurement bits. I mean, as you get in any, like many of you must be playing with Qiskit and other things, and that's how you can, like construct your logical observable. So here, like you can say that this is your logical observable. Let's say if you denote this measurement as your logical observable, because your logical observable in a repetition code is J tensor I tensor I. So we are, like just interested in, like performing a Z measurement here and identity everywhere else. So the errors that anti-commute with the Z will flip the outcome of the logical observable L1. Next, there is notion of error mechanism. So error mechanism is basically a set of M independent error mechanisms, which, which happen with some probability Pi, and they will flip a set of detectors and observables. And they can be used to represent any circuit level noise like nicely. So for example, if you have error here, so that will flip the M1 and that corresponds to detector D1, and also it will flip M2, so the L1 will also get flipped. So here D1 and L1 get flipped by E1. After that, we have this notion of parity check matrices. So here it's just a matrix which, the row correspond to, so you have two kinds of matrices. One is the detector check matrix, and another is a logical observable check matrix. So we talked about detectors, we talked about logical observables. So in your detector check matrix, the row is basically detector column and detector, and the column is basically error mechanism. Similarly, in this L logical observable matrix, row is logical observable and column is basically the error mechanism. And here, basically in your H matrix, Hij equal to 1 if detector I is flipped by error mechanism J. Yeah. And similarly, for the logical observable matrix, it's 1 if logical I is flipped by the error mechanism J, and 0 otherwise. So you get these matrices H and L. And basically, given all this information, like, information about some syndrome which is related to your error, a logical error is nothing but, like those errors which are in the kernel of the H, but are not in the kernel of L. So basically, H is saying that no error, nothing, everything fine, but actually there is a logical, it's not in the kernel of L. And that's what you will call as a logical error. And basically, for all B which belong here in B, I should maybe write here B. Yeah, and this is Hamming distance. That basically gives you distance. So I'm basically reformulating already discussed concepts, like, in the first 2-3 tutorials in this language. And after this, there is notion of detector graph, which is, sometimes people also call, matching graph or decoding graph. And here, basically, you have, all the vertices where they are basically detectors, and, two nodes, they are connected by an edge if they are flipped by some error mechanism. Okay. And there are some this virtual boundaries which corresponds to those detectors which are part of for which there are not more than one there does not exist an error which flips them and any other detector basically. So we have this notion of half edge, and we have also this notion of a regular edge. So these are your half edges, and these are your regular edges. I mean, these are regular edges, and the others are half edges. And the idea is that given this kind of graph, you can employ graph algorithms to do basically a decoding. And one of the algorithms that people use is basically this minimum weight perfect matching decoder, which basically assumes that they have a graph like error model, and given this information about H, L, the prior vector P, and the detector graph G, the error E, basically the task of this MWPM decoder is to find the most probable physical error consistent with the syndrome S. So if some syndrome S, and you would like to find out the most probable physical errors. So basically there are many nice tools which you can use to to do decoding. So there is this nice tool called, like pi matching, like which is on internet. Like you can use this to, do like, decoding. There is another, like tool called STEAM. And in fact, STEAM and pi matching can be combined together for, like building decoders. So the MWPM decoder basically finds a physical error C such that HC equal to S, the speed where S is the syndrome, and P of C is maximum for all C which satisfy the condition 1, which is HC equal to S. Note that, the maximum likelihood decoder, on the other hand, tries to find not only for graph like model, but for a general scenario. And that's why the maximum likelihood decoder, is NP hard, the problem that is try to solve. But these are MWPM, and they are basically they try to solve the problem approximately. So this is an example code, like a STEAM code, which I have, taken, and it can generate basically, the circuit corresponding to, the repetition code. And yeah, you can basically write the circuit, and then you can calculate, how many logical errors you have at a particular distance, and you can increase the physical error, and then you can plot the logical error, and you can do it for different distances, and the place where, the crossing happens, that's what is your threshold. So that's what's considered the threshold of a decoder. And a decoder with higher and higher threshold is basically a good decoder, because for to build fault tolerant memories or fault tolerant, to do fault tolerant quantum information processing, maybe this can make things yeah, like understanding the threshold is quite a fundamental concept. There are other decoders also which I did not discuss, but you can find on internet, like union find decoder, Monte Carlo Markov chain. Those which are based on renormalization group, and neural network based decoder. So there's a nice place, where you can have a look at. Nice. So yeah, decoders are something, which will be I would say very important component of I would say fault tolerant quantum computation. So if we want to achieve fault tolerant quantum computation, it will be very crucial to build I would say better and better decoders. Okay, so now let's talk about some of the connections, basically connections with many body physics and theoretical computer science, and then we will talk about connections with basically black hole physics. Yeah. So this is the first paper which I will discuss here is this nice work by Anurag Anshu, Nicholas Brookman, and Chinmay Nirke, and basically what they showed that there was this conjecture by Friedman and Hastings in 2014, which says that if quantum PCP is true, that conjecture holds, then there is something else called NLTS that will hold. So what is PCP? So PCP basically means probabilistically checkable proof, and for NP basically PCP holds. On the other hand, for in the quantum case, one can ask the same question, do we have a quantum analog of PCP, and that's called that's called quantum PCP, and it has wide implications. It's one of the biggest problem in I would say theoretical quantum computer science, and it has also implication in I would say superconducting physics and so on, entanglement at room temperature and many things. So so basically an NLTS conjecture basically says that there exist Hamiltonians such that none of the low energy none of the states in the low energy subspace, they are trivial. So what does a trivial state basically mean? Trivial means that it can be represented classically nicely, efficiently. So for example, a constant circuit could be considered a trivial state. Like those states which can be represented by constant depth circuit, they can be considered a trivial state. So this NLTS basically means no low energy trivial state, which means there are no so basically one had to show existence of Hamiltonians. Like to prove this conjecture, one had to show existence of Hamiltonians for which all the states which are in the low energy subspace, if you want to represent them, you cannot represent them trivially. I mean, in the language of circuit, they do not admit a constant depth representation. And what this gentleman basically showed that in fact there exist Hamiltonians for which if you want to represent the low energy eigenstates, you require like a depth at least log n. And basically the Hamiltonian which they used, like comes from this paper, this is from the quantum Tanner code. So given this code, like one can construct corresponding Hamiltonian, and then if you try to write the, like you can show that all low energy states basically, if you want to represent them, you will require, like log, and they cannot be represented with constant depth. Then there are also, like other papers, like, which I think started with Kitaev. I think I should have added the paper by Kitaev and others, which show that, like for example, when you are trying to build a decoder, the threshold, basically the point where the threshold, you get the threshold, it corresponds to phase transition of certain, like a statistical mechanical model. So for example, random, like Ising models, if you calculate their, like the point where the phase transition happens, that can give you the optimal threshold for, like the threshold for the optimal decoders. So there are these nice connections which, like people can explore, like, I mean, and there are many more works, I think Sunmon Choi and others, they have also looked at also connection with, random quantum circuits and so on. So there are like a lot of works which are, like which have tried to explore the connection between, like I would say, computer science, like many-body physics and quantum error correction. Now I will finally, like come to discuss the connection with basically black holes. So, so black holes, I mean, many of you must be aware of this picture, and you also know this guy. But can somebody here, like unmute themselves and tell who is this guy here? Like, I mean, who is this person?
I don't know.
Okay.
What's the first letter?
So this person is called Schwarzschild. So corresponding to, like, so this is the guy who like, I mean, he solved the Einstein equation and predicted the existence of black holes. So in black hole, the notion of the Schwarzschild radius that we have, it's in his, like, name. So like you in regular, like regular Newtonian mechanics, we have, let's say if you have some object of mass m1, object of mass m2, the force between them is, like gm1 m2 by r square. Now you can, in such a case, you can calculate how much force, how much velocity it will take for a particle to, like escape the gravitational potential and fly away. So you can write basically the corresponding potential energy, and which will be, like negative, but you can take it on the other side and that will be positive, and you can write the, kinetic energy, and you cancel your m, and then you get this relation. So you have, like v squared by 2 equal to gm2 by r. But what if, the escape velocity is greater than the speed of light? Then you can do a simple calculation, and you see, so that if they are object of mass m, such that, like if any object comes within some radius small r, then, like even if it's light, it will not be able to escape. And such questions were asked, I think, even in 1700 or something. Like, I mean, you can look at the nice book by, not book, like notes by T. Hoof, where he discusses, like black holes and these things, like in detail. Okay. But I mean, this does not capture the physics of black hole. To capture it, you need to actually go to, space general theory of relativity. But before we go to general theory of relativity, one has to go through a special theory of relativity. So in a special relativity, you have basically, like 2 rules. First rule is that, the law of physics is basically same in all inertial frame of reference. And second, speed of light in vacuum, no matter how fast an observer is moving, for them, it's always the speed of light, which is, like c. So 3 into 10 to the power 8 meter per second. So many of you must be aware of this notion of, like light cones, forward light cone, like backward light cones and all this thing. Here is this regular Lorentz transformation. And basically, this is the quantity that you want to preserve. And yeah, nothing fancy. In the general relativity, what we do that the metric that we have here, we replace this by a general metric. And you can carry on the calculation. And for a general metric, when you do the calculation, you get this equation, which is called Einstein's equation. This is what this differential equation has one side, basically stress energy tensor. On the other hand, you have this information about I would say curvature and metric, and this lambda is basically a cosmological constant. So basically you can say that it's the interplay between matter and geometry. So basically I think Wheeler basically said at some point that matter tells geometry how to take shape or something, and geometry tells matter how to move. So basically it's a nice cosmic dance where this left hand side and right hand side basically together are involved. So if you solve it for, let's say, very massive objects which are a spherically symmetric and all, you get the equation, you get this solution. And you can see that there are 2 problems with this one. The first problem is at r equal to 2 gm, and the other is at r equal to 0. And actually, I have, we have taken here c equal to 1. So normally when physicists, when they are doing calculations, they take c equal to 1. You do not put all this. We do not carry all the c all along. So you see that there are 2 problems. One is at r equal to 0, and other is at r equal to 2 gm. And basically these 2 points, they are important point for a black hole. So r equal to 0 is basically that eternal singularity, basically the center of the black hole, and r equal to 2 gm is basically your event horizon. So once you are there, basically God save you. After that you have to you will definitely get inside and hit the basically center of the black hole. So there's this nice lectures on black holes and quantum information which you can look at, and they are basically Daniel Harlow talks about how one can try to analyze all of this from the using tools from quantum information. So I would like to mention this ADS CFT correspondence, which has definitely led us helps us understand basically black hole and many more things using tools from regular quantum physics. So we can have there are 2 different. So ADS is basically nothing but anti-de Sitter space. It has this metric, and basically CFT is conformal field theory. So you can think about it's a field theory which is invariant under basically Poincare transformation, which you can think about glorified version of a Lorentz transformation. So basically transformation plus boost. And on top of that, you can also have a rescaling of the coordinates and some other spatial coordinate transformation. So the field theory that you get there is basically called conformal field theory. And the formal statement of ADS CFT correspondence basically says that any relativistic conformal field theory on R cross SD minus 1. So basically you have some sort of a cylinder, with metric, which is given by here, the metric here of the cylinder, can be interpreted as a theory of quantum gravity in the asymptotically, ADS D plus 1 cross M space time, where M is some compact manifold, which may or may not be, some trivial manifold. Anyway, what it basically says that you have like the boundary, boundary which is, your CFT, and it does not have gravity. On the other hand, the inside is basically, the ADS universe which has gravity, and you can try to understand some physics at the boundary, and you can infer what happens in the bulk, and you can say something about the bulk, and you can try to infer what happens at the boundary. So there is a dictionary which takes, like from the bulk to boundary and boundary to bulk. So it's like a duality, but it's not like, the duality that we study in I would say linear programming or semi-definite programming. It's more like a dictionary which helps you understand physics from two different viewpoint. So yeah, I mean, so you have the CFT and you have ADS, and yeah, like the Maldacena basically, like who is the discoverer of it, he basically calls it, like universe in a bottle. I mean, yeah, that's the cylinder basically. So there's this nice, using this ADS and CFT correspondence, basically people, I mean, there are many works, but I mean, people basically effectively showed that, you can think of that how space and time could be a quantum error correcting code. So basically, let's say you have this state, like so this Q-treat state, and you can encode it into, like, in your logical, like, subspace using this encoding. And when you carry on this ADS CFT correspondence and try to understand what it basically says, that there are three states, like which are your three Q-treats at the boundary, and they basically encode one logical qubit in the bulk. So very nice. And actually, I have not discussing everything but there are also, like, we talked about subsystem codes, approximate quantum error correction codes, and all of these things have found relevance in this kind of ADS CFT correspondence. So the people who are interested, like they can try to, like, the moment you see some nice feature about, like regular quantum error correction code, maybe you can use this dictionary to understand what happens in the bulk basically. And there is some nice, like lectures again by Daniel Harlow on emergence of bulk physics in ADS CFT, where he discusses the basically ADS CFT in detail, and also the role of quantum error correction. So and basically you can think of that black hole is nothing but there are so many errors. So let's say if you have so much error that you cannot correct it, then if you try to interpret the corresponding scenario in the bulk, what you will get is black hole. And what like Patrick Hayden basically says that it's basically a breakdown of correctability when there are so many errors that you can no longer keep track of what's going on in the bulk anymore, and basically you get a black hole. So it's like, I would say, like quite powerful and, like, beautiful theory which helps us see. I mean, error corrections are nice and beautiful, but at the same, I mean, I would say, like, practically nice and beautiful, but it has also it helps understand the fundamental physics, I would say, at a very deep level. Okay, so then I would say, yeah. So that's it. Like, so I will now summarize. So we talked about, like different decoders, like, maximum likelihood decoder, minimum weight perfect matching decoder, union find. I mean, we talked about MWPM, and we mentioned all other decoders. And we also talked how can you calculate the threshold. After that, we also, like discuss this NLTS thing, and basically NLTS conjecture is true. So we still don't know whether quantum PCP is true or false, because if it were false, then quantum PCP would have been false. But basically, these three people basically showed that, like NLTS is true. There are also connections between, like threshold and basically phase transitions, like of some statistical mechanical model and so on. Then we also discussed how a space and, like, the relation, the ADS CFT, black hole, and like the relevance, the relation with quantum error correction. So that's it. I am very happy that like we managed to reach the end of the tutorial session, and I will just there is this small like poem which ChatGPT wrote in the honor of last tutorial. So those who are interested, basically they can read, and there is small haiku. Like some of us like haiku a lot, and basically this is also written by ChatGPT. So it says the quantum impulse errors corrected, we saw journey complete. So with this, I will I think we can put close the session, and yeah, like maybe Chanvi, you can stop the recording, and we can start the like uh, regular discussions.